Hey, welcome back to Fat Mama Physics. In this video, we are going to do an example on electromagnetic induction, in which here we have a magnet. It's going to fall from rest through a coil of wire, and we want to find a potential difference across the coil with a datalogger. So this is in fact an IB question, so let's kind of go through the thinking behind each of these parts, okay? So here we have a graph that shows the variation of time of the potential difference, that's what PD stands for, potential difference, across the coil, okay? Okay, as we go down here, explain with reference to Faraday's and Lenz's law the shape of the graph. So if I remember correctly, this was a 5-mark question, so we need 5 good points. So if the question says with reference to Faraday and Lenz's law, you probably have to explain that to some degree. You have to probably define that. So I am going to, maybe I'm going to have to write it up here, okay? So let's write it up here. First of all, we know that Faraday's law is essentially that a change in the magnetic flux linkage through a loop of coil of wire is going to produce an induce an EMF across the wire. So that is Faraday's law, in which you have to talk about a change of magnetic flux linkage, or you can actually, it's better to say that the induced EMF is going to be directly proportional to the rate of magnetic flux linkage change. So the induced EMF is going to be directly proportional to the change in magnetic flux linkage. Okay, so that's di phi over here. Okay, so that's going to probably give you the first mark, okay, because it's a 5-mark question. Lenz's law talks about how the direction of the current is going to oppose the change in the magnetic flux. So that is basically talking about the direction of the current. Okay, so I've actually typed both of them out so that you can kind of see, instead of my chicken scratch, the induced EMF is directly proportional to the rate of change in magnetic flux linkage. This is your Faraday's law. Okay, so that's Faraday's law here. This one down here talks about Lenz's law. The direction of EMF is induced so that the magnetic field produced by this current will oppose a change in the magnetic flux through the coil. So we're going to use that to talk about the shape of the graph. Okay, so you might notice that there are 2 spikes. One of them is in one direction, and then the direction here switches. The EMF switches to the other direction. So that's one thing you have to talk about. Okay, so notice that there's a switch here. The other thing you probably notice is that the peak at each point here is different. The first peak hits 0.6 volts. The second peak hits 0.8 volts. So we have to explain that as well. There's also another little interesting difference here. If you take a look at the width of each peak, or the base of the peak, is a little bit different as well. So we have to talk about that ultimately. So let's talk about the direction first, because that's probably one of the easiest things to explain here. So why do we see a difference in the change? So if we take a look at this magnet, and you probably have to use the right-hand rule with me on this one, and because my camera is mirrored, that's not going to be very fun, so you have to do it with me while I give you instructions. So take your right hand, drop your pen, thumb up, and your fingers are going to curl around that thumb. When the magnet approaches the coil, and to do that we probably will have to determine some the north and south poles here. So let's assume that's the north pole, and that side is going to be our south pole. And based off of our knowledge of magnetic field lines, we know that the magnetic field goes out of a north pole and comes back in onto the south pole. So this is kind of what the magnetic field lines look like. So this is a simplified drawing, but essentially we have the magnetic field going through the coil like this. So we can use that to look at how the flux is changing as the magnet is approaching. As the magnet is approaching, so you're gonna have your thumb out. The magnetic field or flux down the coil, so in the downwards direction, will increase. So to oppose that change, the current must produce a magnetic field in the opposite direction, which your thumb is going to point up. So that you'll notice that the current is going to curl in the well, let's see. If you're looking at from the above, it looks like it is curling counterclockwise. So this is going to be a little bit tricky. So you kind of have to use your paper there, and you have to curl your fingers in the direction of the coil. So the coil kind of curls upwards as you curl into and back out of the page. So you'll notice that as you do your curl, you should get your current kind of coming up in this direction to begin with. Okay, so as the magnet is moving down, and that's just the first part, the current is going to go through the datalogger in the downwards direction. So that's when it first approaches the coil. We kind of have to now figure out what's going to happen as the magnet is leaving the coil, which is going to give us the second half of that drawing there. So let's look at the magnet down here. And know it's going to look a little messy, but as it is leaving, the south pole is the butt of the magnet is going to face the coil. So what does that look like in terms of the magnetic field lines? The magnetic field lines are going to go towards the south pole, so it's going to go in that direction. So using my pen, it's going to go down like this, and then out of the North Pole like that, okay? So I'm not going to continue that drawing. You kind of get the idea. The magnetic field is going downwards still, but as this magnet is leaving the coil, the magnetic flux going down is going to be reduced, okay? So because it's going to be reduced, the current produced must oppose that change, meaning that the more magnetic field has to be supplemented in that direction, if you kind of think of it as this way, to compensate for that loss. To compensate for that loss, if you put your thumb downwards, then you are going to curl your finger, and as you look from the top, it looks like it's in the clockwise direction. So this is going to be a little tricky. As you curl your fingers around the coil, like it's going into the page on the, if you're looking on the page, don't look at me, look at the page. Okay, if you curl your fingers in that direction, it looks like the fingers go into the page on the left side, and it kind of exits out this way. So what happens is that you get an opposite direction in the current as the magnet is leaving the coil. So I'll use a different color pen here. Okay, so in the second half, the current is going to go in the opposite direction. So that explains why you get a peak in the beginning. This is when the magnet approaches the coil, and when it's about to leave the coil, it's going to generate the EMF in the opposite direction. So let's use some words to explain that. Okay, so here is the second part. As the magnet approaches the coil, you'll see an increase in the magnetic flux. And you're thinking, you just assume the direction of the polarity of the magnet. You can try to work it out with the south pole on the bottom. If the south pole is on the bottom, then your field lines are going to go upwards. And as the magnet is about to leave the coil, you'll also have a decrease in the magnetic flux going upwards because the north pole is on top. So regardless of whichever pole is facing what direction, you're still going to get an increase of flux as the magnet enters the coil, and a decrease in flux as the magnet leaves the coil. So with the increase and decrease, the change that opposes that is going to change. So the direction of the EMF you're going to get will be in opposite direction. So that's probably going to give you the third point. The next thing we have to talk about is the stark differences in the EMF here. And the one thing you probably notice is that this magnet is going to fall vertically from rest. So there's going to be some free fall aspect of this, and assuming this is falling with some sort of acceleration due to gravity, this magnet, as it is going through the coil, will accelerate. And because it will accelerate, the speed that it enters the coil is going to be less, or actually, the speed that the magnet exits the coil is going to be greater than the speed that the magnet enters the coil. So because there's a difference in the speed, the rate of change in flux is going to be larger on the bottom versus that it's going to be on the top. And because of that, you're going to see, we know that the rate of change in flux is going to give us the induced EMF. The rate of change is larger, which means the EMF produced later is going to be higher than the one produced earlier. So therefore, the second peak is higher than the larger than the first peak. So here I've written, since the magnetic speeds up as it drops, the rate of change in magnetic flux increases for the second one versus the first one. So the second peak is going to give us a larger absolute EMF versus the first peak. And this is also going to help us explain why the width is a little bit, why it's the width is greater for the second one versus that of the first one, because the magnet leaving the coil will take less time than the magnet entering the coil, since the magnet speeds up. Okay, so it also explains why the time to generate the second peak is smaller. The width and time is smaller versus the one entering, since it will take less time to leave it versus entering it, since it is in free fall. Okay, phew, that's that's all the concepts that you have to mention in a 5-mark question. And I took the luxury of being able to fully explain everything there, but yes, I'm so sorry. Good luck on trying to explain that in a condensed manner on a given space of 5 marks. But the reason why I wrote all this out, so that I can hopefully be able to communicate this, or may help you understand why this is the case for you. Okay, so that was just one question, AI. Second question, let's hopefully these questions will go a little faster. The coil has 1,500 turns. That's going to give us N value there. Calculate the magnitude of the maximum rate of change of magnetic flux. So the rate of change of magnetic flux is going to be di phi over di time. So, or the change in flux over the change in time. So that's what we're trying to do here, okay? So we do have the EMF. The EMF is equal to the N number of coils times the change in the magnetic flux here. So all we have to do is just to solve for this part here, which is what they're asking for. And it's looking for the maximum, meaning that we're probably going to take the maximum EMF. The maximum EMF is 0.8 volts. Okay, that's the maximum. So we're going to use a maximum. We're going to use N, and we're going to use that to find di phi over di t. So EMF max over the N value is just 0.8 volts over 1,500 turns. And that's going to give us the 5.3, rounded to two significant figures, which is 333, but two sig figures, 5.3 times 10 to the power of -4. And the flux is going to be... Since it's the rate of change of magnetic flux, this is Weber per second. So that's to the power of -1. Okay, so there we go. That's the first, that's 2. Okay, next up, the magnet now is suspended from a spring. Oof. The magnet is displaced vertically and starts to oscillate in and out of the coil. A sinusoidal alternating current of RMS value for 280 nanoamps is induced in the coil. State in words on how the RMS value of the alternating current relates to a direct current of 280 nanoamps. So the RMS, really what that is saying is that across a resistor or across a load connected to an alternating source versus to a direct source, the effective current that goes through that resistor is still going to be 280 nanoamps. So that when you're calculating for the power or the power dissipated, that's exactly the current that's going across the resistor. So how to put that in words? Okay, so the power dissipated across the resistor using direct current will receive 280 nanoamps. So connected to the direct current, it will have 280 nanoamps, and to help you find the power dissipated, and it's going to be the same effective current that the resistor will receive when connected to an alternating source when you're trying to calculate for the power dissipated. Okay, so something to that effect. Okay, next one. The coil has a resistance of 1.5 mega ohms. Calculate the peak voltage across the coil. So we have here, this gives us the resistance. We have an alternating current, which is RMS here, 280 nanoamps. And we want to find the peak voltage. So again, we can't find the peak voltage from the RMS value for the current. We can use the RMS value of the current to find the RMS value for the voltage. So we can do that first. So VRMS, which then we can later use to find the peak voltage, but for this one first, is going to be our current, RMS, times the resistance. So 280 times 10 to the power of negative 9 amps, and 1 times the resistance, 1.5 times 10 to the power of 6 ohms, is going to give us one hunk of a number. This is 4.2 times 10 to the power of negative 11 volts. So to convert that to the peak voltage, we know that the peak voltage is, the peak voltage divided by the square root of 2 is going to give us the RMS voltage. So if we take RMS and we multiply by the square root of 2, we're going to get the peak voltage. So we take our previous number and we times the square root of 2 is going to give us 5.939 or 5 point, how many sig figs? 2 sig figs. So 5.9 times 10 to the power of negative 11 volts. So very tiny, considering it's a big resistor. I think I made a calculation mistake here. And it looks like this is 4.2 times 10 to the, it's just 4.2, 0.42 actually. So let's do a quick change here. So that is 0.42 volts multiplied by the square root of 2 is going to give us, okay, that's the same. Good. 0.59 volts. Just double checking. Okay? So, there we go. That is question B2. Okay, hey, this is the last question. Okay, almost there, guys. Explain what effect the generation of the current has on the oscillation of the magnet. Interesting. So here we're going to look at the magnet when it first enters the coil as part of the oscillation. After the magnet enters the coil, it's going to come back out of the coil in the same direction. So we're going to look at both cases to see how the magnet, how the motion of the magnet is affected by the coil itself. I did part of this in the first question, which the magnet is entering the coil, but this magnet doesn't actually go through the coil. It actually comes back up since it's in oscillation. So we are just going to arbitrarily decide that this side is the north. It actually doesn't matter if it's the north or south. The effect is the same of the reduction and the gain in magnetic flux, but we just want to give it some reference point to help us explain this question a little bit better. Okay, so the magnet entering the coil means that there's going to be an increase in magnetic flux going through the coil downwards, since the field lines go out of the North Pole and back into the South Pole, like this. So we're going to get an increasing flux going into the coil, and we already, from the previous question, figured out that the current is going to go through the data logger in the downwards direction. So you can refer to that explanation earlier in the video. So when the magnet first enters the coil, we're going to have an induced current going down the data logger. So if we want to, so whenever we have a current through a coil, what happens is that it creates a temporary magnet called an electromagnet. So this electromagnet here, if we use our right hand rule, if we kind of use our fingers, so this is drop your pen, okay, use your right hand, take your fingers, curl around the coil in the direction of the current. So it looks like it's going to kind of go up and around from the right side. So that's what I'm going to do with my fingers. I'm going to curl around, and my thumb is going to point upwards. Okay, so my thumb points upwards in the direction of the induced magnetic field, which is in fact the exact direction that which we have to replace. We have to compensate for. So this creates a temporary magnet, electromagnet, in which the North Pole is on closer to the top end of the coil, and the South Pole is on the bottom, effectively, since the electric field lines would have to leave in the direction and come back through the bottom. So the magnetic field through this produced through the coil is in the upwards direction. So notice that clashes with the magnet coming in. So because of that repulsion effect between the two poles of your magnet and temporary magnet, we're going to get this magnet, as it's coming in, is going to be slowing down. Okay, it's going to slow down as it is going into the coil. So what happens when the magnet is leaving the coil? So let's use a different colored pen. So let's say we have the same magnet, but then it's going to leave. So as it is leaving, again, the North Pole is still going to be in the same direction, but in this case, the field lines go, even though they're still in the same direction through the coil, they're going down into the coil. But in this case, it is decreasing as it is moving further away. So to compensate for that decrease, the current induced has to be produced so that the magnetic field produced by the induction is also in the downwards direction to compensate for that loss. So if you take a look at the coil and the wire, it's going to curl around. So I'm going to kind of curl around the back. And the way to curl around the back is for the current to kind of go down this way, curling around the back and back into the front onto the right-hand side. So this allows your thumb to point downwards, meaning the current through the data logger is in the upwards direction. So because of that, the magnetic field produced by that current is going to point in a downwards direction. So the downwards direction, it means that effectively you're going to have a coil. I should have made two diagrams of this. So you have a coil in which the electromagnet produced is going to have the north end on the bottom and the south end on the top. So effectively, sorry, I guess I'll draw it again. So here's my coil, and the magnet is leaving now. So with the north end and the south end with the south end on top, because of this attraction between the North Pole and the South Pole, the magnet is going to want to be pulled back into the coil, which means it's going to slow it down as it is moving up. So overall, the magnet will get slowed down as it is oscillating. So the effect of that is it's going to receive some sort of damped oscillation. It's going to be damped over time. We call this damped oscillation, and which means that the mechanical energy of this magnet is decreasing over time, meaning this mechanical energy is going somewhere. Well, it looks like a current is being produced, which is electrical energy. So all this mechanical energy is getting converted into electrical energy in this through the data logger with the current produced. So all of this energy is will be dissipated, I guess, in the form of heat through whatever load is in this connected in the current, but that's where it will get dissipated into. It'll be dissipated into the coil as current and used to I don't know, heat up due to Joule heating of some sort of resistance in the circuit. Okay, so dissipated energy. So it's dissipated into energy in the coil due to the current produced, and so that it will explain. Yes, so because of that, the magnet is going to slow down over time. Okay. And this has a lot of applications, unique applications, which has to do with damping. And in this case, we have a coil, but in other applications, if you have something that's oscillating or moving in usually something called an eddy current is produced. An eddy current, it takes off a similar effect. It has the effect of damping of any sort of motion to cause things to slow down, such as used in braking, in roller coasters, and even electric balance scales. Okay, so all sort of this application is used in many places for that effect. Okay, so the eddy current, but this one is it's very direct. It's just producing electromagnet. So the eddy current is kind of less direct, but it achieves the same effect, which is damping. Okay, so I thank you for bearing with me through this entire question, multi-part. So job well done for staying around, and I hope you got something out of this video. I wish you the best of luck, and Fat Mama Physics signing out.